we're going to talk about something called exponential functions. Have you ever heard like somebody go, it's growing exponentially? You usually see it like some sort of science dorky math movie that I just love. Yeah. The population is growing exponentially. Oh! Yeah, you've ever, no? I'm the only one who watches dorky, sciencey math movies? Apparently. Yeah, I don't watch that crap like Made in Manhattan. I watch that crap like Star Trek or things like that. Anyway, we're going to talk about exponential functions. If you talk about exponential growth means it's growing at an exponential rate. We need to talk about what exponential even means. You might have heard that if you're in science class, growth of bacteria. You ever study growth of bacteria? Mm-hmm. Starts with like one of them, right? Mm-hmm. One splits into two of them. Two of them split into four of them. Four of them split into 16 of them. Then 16 squared is 256 of them. And then 1,020. It keeps going faster and faster and faster and faster and faster and faster and faster. You know, I did that wrong, actually. It's multiples by 2. I squared everything, I think. My bad. It should be 2, 4, 8, 16, 32, 64, 128, 256, and so on and so on and so on and so on and so on. I think I squared all those numbers really, really, really fast. Anyway, but it's growing because every time those two little bacteria are splitting, right? Same thing with rabbits. You ever heard they're breeding like rabbits, which means that those rabbits are really growing fast because you start with 2 rabbits, all of a sudden you have more rabbits, and they're breeding, and then you have more rabbits, and they're breeding, and you have more. That's exponential growth. Populations tend to grow exponentially into a limiting factor where the population eats all the food and then things start to die off, or disease comes in and kills things off. It's typically exponential growth, or modeled by exponential growth. So we got to talk about an exponential. Every exponential is of this form. You're going to have b to, now this is going to be weird, right? Because normally we have like x raised to some power, right? X to the 1/2 power will be a square root. X to the 3rd power will be a cubic. X squared is a quadratic. Now we have this. We have some exponent that is our variable. B is called a base. It's a number, like 2 or 5 or 1/2. B is our base. B does not change for your exponential for whatever I give you. So if I say B is 2, that it's going to be a 2 for as long as I tell you. Also, it'll be greater than 0. It won't be negative. X, our variable, is actually our exponent. So exponentials have a really unique look to it. Instead of having a variable raised to a number, we now have a number raised to a variable. That's a weird idea, right? We've got this number raised to something that's changing. So an exponential function is going to look like this for us. We're going to have f of x equals b to the x. Now, I would like to show you a couple graphs to see the difference between these things. I'll put them up on this side of the board so we see the difference between them. We're going to find out how exponentials actually look graphically. So I want to graph 2 functions. We're going to do them on 2 sets of axes so we see the difference here. 3 to the x and 1/2 to the x. Hey, first things first, can you identify that these 2 functions are in fact exponentials?
Yes.
What's your base here?
3.
Good. What's your exponent?
X.
That means exponential. It's a variable. The other one, what's your base?
1.
Good, to the x. You'd have to have that fraction in parentheses saying the whole thing's being raised to the x power. Now, we're going to make these with a table because we have no other way to do it right now. We don't know what these look like. So x, g of x x f of x. Now typically, we'll pick 5 numbers. Pick 5 numbers on each of our graphs. So let's pick, we'll start the positive side first, so it'll be easier. 2, 1, 0, negative 1, negative 2. Do the same thing over here. 2, 1, 0, negative 1, negative 2. Oops, that's not a 2. Now help me out with this. If I say my variable takes the value of 2, what's that mean for my function? How can you represent that? So I plug in 2. What are you going to do? How much is it going to be if I plug in 2 here? It's going to be 9. 2 squared is 9. You follow that? 2 squared would be 9. How about 1? If I plug in 1, how much am I going to get? That'd be 3 to the first power. How much is that? How about 0? If I plug in 0, what's 3 to the 0?
1.
Yeah, don't tell me 0, right? It's not. It's 3 to 0. Anything to the 0 power gives you a 1. That's interesting right there. Now, here's the cool ones. Ready for the cool ones? Negative 1. If I plug in negative 1, I'm actually going to do the work here for you. If I plug in negative 1, that's 3 to the negative 1. Do you follow that? 3 to the negative 1 doesn't mean negative 3. It actually means 1 over 3. With me there? That's weird, right? Is it negative? So does a negative number being plugged in actually give you a negative answer?
No.
Oh, that's strange. That's kind of cool. That's weird. It's actually, here's what this is going to do for you. Check it out. Is this graph ever going to be negative?
No.
No. Not unless you have a negative in front of that. Then it would be reflected. But no. And negative 2 would be 3 to the negative 2. That's going to be 1 ninth. You see the relationship? Look at 2, 9. Negative 2, 1 ninth. That's cool. It's kind of interesting. If you plot these points, notice that I do have points. I plug this in, I got, let's see, 1, 2, 1, negative 2. If I plug in 2, I got out 9. If I plugged in 1, I got out 3. If I plug in 0, I got out 1. Are you okay with these 3 points, folks? Nod your head if you are. Feel okay with that? I'm not getting a whole lot of head nods. It's either yes, well, I mean, I did that backwards. It's either yes or no. It's either yes or no. Are we yes or no?
Yes.
Okay, so these are just our points here. This side of the graph, do you see what it's doing? Is it straight? No, it's going. In fact, if you plug in 3, what's 3 to the third? You'd already be at 27. Plug in 4. What's 3 to the fourth? 3 to the fourth. 3 times 3 times 3 times 3 is? 81. 81. If you plug in the number 4, you're going to be at 81 already. That's off the chart. That's way up there. That's way up there. Are you seeing what it's doing? It's growing so fast. This side of the graph looks like this. Way up there, really, really fast. Faster than a quadratic. Quadratic's always a power 2, right? But this one is saying you're taking a number, you're increasing the power. Man, that's growing fast. That's really fast. Now on the other side though, check it out. Can you plot negative 1, comma 1/3? And here's negative 1. 1/3 is up or down? Up, but just a little bit. That's like right there. That's 1/3. You with me? Negative 2, we got 1 ninth. That's almost on the x-axis. Now let me ask you a series of critical thinking questions, okay? Firstly, again, are you ever going to have something below the x-axis? No, not unless there's a negative in front of it. Second one, is this ever going to touch the x-axis? You're going to get really close, but it's never going to touch it. Think about it. 3 is going to be 1 over 27. 4 is going to be 1 over 81. 5 is going to be 1, I don't even know anymore, but you take 3 to the 5th, put 1 over that, it's going to be really, really, really close, right? But it's never going to touch it. This is called being asymptotic to the x-axis. It has an asymptote here. It's going to get really close, but never touch it. So this side looks like this. It doesn't go back up, that's a mistake. It keeps going along the x-axis, getting really, 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 really close to it. Here's a sound effect for a exponential function. It goes. That's how. My upper register is a little gone on that one. Try one more time. Lips are dry. Do you hear it? It goes up like that. I want to see what the fraction does, and then we'll call it a day. We'll be out of here. Remember that clock's a little bit fast. So if I plug in 1/2, check it out. 2 to the 1/2. 2 to the 1/2 gives you, that would be 1/2 squared. Oh, I did that backwards. I said it backwards. 1/2 to the second. 1/2 to the second power is going to give you 1/4. Do you see how we're getting 1/4 out of that? 1/2 to the first power. Well, anything to the first power just gives you that back again. How about 0 to the 1/2 to the 0 power?
1.
Yeah. Oh, that's weird. We're going to get 0, 1 again. Can you imagine this for every exponential? If you have an exponential up here to the 0, you're always going to get out 1, right? So 0, 1 should be on every one of our graphs unless we shift it around. We'll talk about shifting later. Now, -1, that's 1/2 to the -1 power. Here's what this does, watch carefully. If you have a fraction to a negative power, what you do is you can flip that fraction, reciprocate it, and it changes the sign of that power. So we would have 2/1 to the first or the number 2. Same thing would happen here. 1/2 to the -2, you're going to get 2/1 squared. You flip your fraction, it changes the sign of the exponent. That's an exponent rule that we covered a while back. How much is that going to be? 4. You see the same relationship, right? 1/4, 4. We'll graph it real quick. If I go over to 2, 2 gives me 1/4. That's right there. If I go to 1, it's giving me 1/2. That's slightly higher. If I go to 0, it's giving me 1. That's here. If I go to -1, check this out on the board. If I go to -1, I'm getting 2. And if I go to -2, I'm getting 4. Are you all okay with those points? Do you see what this is doing? Do you see what it's doing? Is it going the same direction as this?
No, it's true.
So a couple questions, 2 more questions. Is it ever going to be below here?
No.
No. Is it ever going to touch the x-axis?
No.
This looks almost the opposite of this. It's almost like a reflection. Different number. That's it. That's our exponentials. This one goes. This one goes. That's the idea of these exponentials. If our base is greater than 1, if our base is greater than 1, we'll have this. It will climb. If our base is less than 1, it will fall. So whole numbers or fractions greater than 1, it's going to look like this every time. Fractions less than 1, it'll never be less than 0. It's never negative. It will fall like that. How many people understood these ideas of our graphs here? Good, okay. So last time, let's get this over with? All right. No, I'm just kidding. Last time we were talking about functions. Specifically, we talked about inverse functions. That's what you did your homework on. Did you guys do okay on your homework?
Yep.
Yeah.
Switching to x and y, right? You remember how to do that? Because we're going to look at that in just a little bit. Now, we talked about one specific function towards the end of our day, and that was exponential functions. And the idea was, instead of having a variable to a number exponent, like x to the second, x to the third, we now have a number, which is a base, raised to a variable, which is our exponent in this case. So we have these things as our exponential functions, like 4 to the x, or 1/3 to the x, or 3/2 to the x, or 2 to the x plus 3, or 1/3 to the x plus x minus 2. Those are all exponentials because we have a number base, and then our exponent actually has a variable in it, and that's interesting. Now, we did talk about 2 things. We either have one of 2 shapes of graphs for our exponentials. It either goes, or, do you remember talking about that last time? It's one of these sweeping curves that grows really quickly or declines really quickly and then flattens out. That's our 2 types of exponentials. I need you to be able to tell me which one of these, each of these would look most like. Now, of course, this is just kind of a generic thing saying if our base, which is our b, is greater than 1, we've got this basic shape. If our base is less than 1, we have this basic shape. Notice how in each case we go through the point 0, 1 and we go through the point 0, 1. Do you remember why that is? Do you remember why that is? Or in other words, let me remind you of this. What would happen if I plugged in 0 here and here and here? In every case, what am I going to get?
1.
What's anything to the 0 power, folks? That's why we're always going to get the point 0, 1 unless we shift these around. Are you with me on that? It's always going to go through 0, 1. That's why we have that point, that point. Now let's go ahead and refresh your memory on this. Let's call this graph number 1 and graph number 2. Can you tell me, ladies and gentlemen, what graph does this one look most like? 1 or 2?
1.
Why 1?
Greater than 1.
So this 4, that's saying, oh yeah, that's our base, right? B's bigger than 1, it's going to be climbing like that. This is most like graph number 1. Now somebody else hasn't spoken yet today. How about this one, 1/3 to the x? 1/3 to the x. Is that most like graph number 1 or graph number 2 and y? Number 2, why? Good, that's a fraction. It is a fraction, sure, but it's a fraction less than 1. So this would most look like number 2. It's going to go just like that. We studied y last time. How about this one? This one can be kind of tricky if you don't really understand why these work. Is this more like graph number 1 or number 2? Why not number 2? It's a fraction like number 2. Aha. So this is like 1.5. This is 1.5 raised to the x power, not some fraction less than 1. This is most like graph number 1. The larger the number, the more dramatically that will climb. The smaller the number, the bigger the denominator, in other words, the more dramatically this will fall. How many people feel okay with this so far? Okay, now our last two, I want to show you that just like we did in the last chapter and in chapter 8, we can shift these things around. Let's look at this one. Again, is this more like graph number 1 or 2 from over here? What do you think? Yeah, definitely 1, because that's greater than 1. Are you following me? Now, that plus 3 at the end of your graph, that plus 3 at the end of your function there, that should equate to some sort of shift. Do you notice how it's not within the function, it's not connected to that x. It's not in the exponent, it's 2 to the x, and then at the very end you have that plus 3. Do you guys see what I'm talking about? That plus 3, do you suppose that shifts it up, down, left, or right? What do you think? That's up, just like any other shift. This would shift it up. Now here's how you do that. If you normally would cross here at this 0, 1, remember how they all cross at 0, 1? This is going to shift it up 3 spots. Where's it going to cross now? 0, 4, yeah, that's going to cross right there. So we would shift our function up 3 spots because that would be a shift up. It's at the end of your function, that's a shift up or down, depending on whether it's plus or minus. How many people feel okay with that one? Yes, no? Do you remember the shifting, how we shift those parabolas up and down, left and right? At the very end, that plus 3, that was at the end of your function, we're shifting this up 3 spots. We're basically taking this one, shifting up 3 units. Now the last one, this g of x equals 1/3 x minus to the x minus 2. The first thing I need you to understand is which graph it's most like. Would you say this is most like graph number 1 or graph number 2? Yeah, definitely 2. Why is it most like graph number 2? Okay, great. So you're identifying, you guys sound like you're identifying the shapes pretty well, yes? So this is definitely like graph number 1, b's greater than 1. Definitely like graph number 2, b's less than 1, it's a fraction less than 1. Now, this minus 2, does it look different than this plus 3? This plus 3 wasn't attached to the exponent, was it? It wasn't within the function, it was after the function. It said you have 2 to the x, then after you do 2 to the x, you're going to add 3 to it. You with me on that? That's a vertical shift. That's saying you're going to find out what this guy is right there and add 3 to the height of it. That's shifting it up 3 spots. This one, on the other hand, says, okay, you're going to subtract 2 from your x before you even take that to the exponent. You with me on that? That's not a vertical shift. That's a horizontal shift like we've studied before in chapter 8 and chapter 11 again. Now, do you remember, do you guys see that that is within the function? That is like you have this exponent right here with some parentheses around. That's what that's saying. Do you remember what minus did if it's within the function? Was it left or was it right? That was to the right. It is like it was the opposite. It's actually slowing down the function. So if it normally started here, remember that we're on this graph. If it normally started here, it's going to start later. It's going to start later. So this would shift it 2 spots to the, what was it again, left or right?
Right.
2 spots right. So if we normally cross at 0, 1, check this out. If we normally cross at 0, 1, we're now crossing at 2, 1. Do you see why we're crossing at 2, 1? It's shifting this spot, look at this spot, this whole graph, but we're going to look at that one value 2 spots to the right. 2 spots to the right. Are you guys okay with that one? So we'll redraw our graph. It just now has to go. Now we don't know exactly where it crosses the y-axis. We'd have to do some work on that. Plug in 0. You're actually going to get, let's see, 0, -2. You're going to get 9. You get 9 out of that, so we'd cross up here at 9. But basically, I just want you to understand that we can still shift our graphs around, is what I want you to get across from this. Okay, not exactness. I want you to be able to identify what type of graph you should be looking at and how to shift these things. If it's after the function, again, we're vertical. If we're within the function, of course, we're going to be horizontal, and it's kind of opposite of what you want to think it is. How many people understand our shifting so far? Do you see the similarity between chapter 8 and 11 and now what we're doing here? It's the same stuff's getting repeated, folks, the same stuff. Now, the last thing we have to talk about in this section is how to solve these exponentials. This is going to be kind of interesting. It's kind of fun. It's like do you guys like puzzles? Then you're going to love this. Ready for it? You know you're going to be doing puzzles over Christmas break, right? Sitting there doing. Now you can do math puzzles before Christmas break. It's even better. I mean, there's no missing jigsaw pieces, you know. You don't have to bend a corner and bite one off to make it fit. This is going to work perfect because it's math. Awesome. Here's the idea of solving these exponentials. Here's the idea. I want you to assume that we have b to the x equals b to the y. So basically, our bases are identical. The bases are the same. Are you with me on this? Firstly, can you see it's an equation? Yeah, we get an equal sign. Great. Can you see the bases are the same? If the bases are the same, what do you know about the exponents? And if you can't answer that right now, let me give you a specific example. Let's say 2 to the third equals 2 to the question mark. And you don't know what that is. What's the only possible number that could be to make this equal?
3.
3. If it's 4, you're going to have 8 equals 16, right? If it's 2, you're going to have 8 equals 4. The only thing that this could possibly be to make this equal is also a number 3. Are you with me on that? That's it. That's the only thing it could be. So here's what this says for us in general. If our bases are equal, then our exponents absolutely must be equal. Does that make sense to you? If you have this, then it's very nice. If your bases are the same, then your exponents must be equal. That's the only way that's going to work. If 2 to the third equals 2 to the I don't know, well, you do know. The only way this can possibly equal is also a 3. That's the only way. How many people feel okay with the idea of this? If our bases are the same, our exponents, I didn't get a whole lot of hand raising, so if you have questions right now, it would be a perfect time to ask. Yes? Oh, question? No question. Any questions on that one? Do you get the concept that if the bases are the same, the exponents have to be the same? I mean, try plugging in any number besides 3 there and see if they're equal. Are they going to be equal?
No.
The only way this is 8, right? The only way this is also going to be 8 is if you have 2 to the third. If you have 2 to anything else, it's not going to be 8. You have something different. That's the whole idea. Now, how we're going to use that, is with problems like this. 2 to the x equals 16. Yo, wait a second. 2 to the x equals 16. I'm trying to solve for x, right? But really, we have no algebraic way to manipulate this problem to solve for x. What are you going to do? You're going to divide by 2? That's not going to work because x is still an exponent, right? You go, well, wait a second. How do I solve for x in this case? We're going to use this fact. So here's your ultimate goal when you're dealing with exponentials. This is it. This is all we have for now. In just a while, we'll have something else. But for now, all we have is the idea that if you can make your bases the same, listen carefully to my words, if you can make your bases the same, then you know for a fact that your exponents are going to be equal. You follow me on that? If you can make your bases the same. So our goal is you're going to try to make the bases equal. Make the bases the same. Now, you got to buy into this fact before you can do this problem. So if you don't buy into this fact, this is not going to work. Do you buy into the fact that if the bases are the same, then the only way these two things can actually be equal is if the exponents are equal? Do you follow that? Okay, if not, this isn't going to work. Okay, if you're like, well, I don't understand that, well, then you're not going to get this part. So if you don't, if you're like, I really don't get it, do you have any questions for me about that one? Are you guys okay with that? Give me a head nod if you are. That the only way these two things are actually going to be equal, and the bases are the same, is if those exponents are also the same. It has to look identical. You follow me? It's got to be the same thing. Now, so if our goal is to try to make the bases the same, do I have the same bases here right now, the way it is?
No.
That says 2 to the x, that says 16. Well, what I need to do is somehow make that into a 2. A 2 to some power. Do you follow me? Because our base over here, that's given. We can't change that one right now. That's 2 to the x. This one, though, that's 16. Can you write that as a base of 2 to some power?
2 to the 4.
2 to the 4. So if we can translate this thing a little bit, we got 2 to the x equals 2 to the 4th. Is that still the same thing as 16? Well, that's awesome. You know why that's awesome? Well, look at the problem. Do you have the same base? Right now we know that if the bases are the same, the exponents must be equal. Do you follow me on that one? So why does it work for us? Well, shoot. I mean, if you have this, look at this statement. It looks identical to that, except in this case, b is 2, and your y is 4, right? Well, look at the next thing we could do. Essentially, we can drop our bases. Do you see that? If the bases are the same, you can drop your bases. You go, oh, b to the x equals b to the y. That means x equals y. 2 to the x equals 2 to the 4th. That means x equals 4. You're done. Isn't that kind of neat? Yeah, that's cool, right? What's next? Nothing. Nothing. That's it. It's just manipulating those bases to get them to be the same in this section. That's your whole idea here. Now, can I get a little bit more complicated than 16? Sure. Sure, 16 is pretty easy, right? I hope. How many people are able to understand that idea? Good. Notice how you had to get that before you can get this, right? You have to understand that concept. Otherwise, you're like, what's going on with the 2? It's magic, Harry Potter. You have your math wand out. And you're just, no, this isn't magic, right? This is using this fact right here that if the bases are the same, our exponents have to be equal. That's the whole idea. I'm not Harry Potter. I'm more like Voldemort. I've already told you this.
Yeah, but now it's not.
Except I don't have that nasty looking weird snake face thing. I hope. Let's try another one. Do a couple more together. I'll give you a few to do on your own. We'll talk about an interest problem. It'll be very interesting. And then we'll continue. 5 to the x equals 125. Are our bases the same right now? No, we have 5 to the x equals 125 to the first. That's not going to work for us. We want 5 equals 5 as far as the bases go. Can you change 125 into a power of 5? 5 to the third. Great. So our whole goal here is to try to make this equal this, our two bases. 5 to the third, that's the same thing as 125. How much is x? And you're done. As soon as you make those bases the same, you set your exponents equal to each other. Four to the x equals 8. Okay, well it's definitely an exponential because our variable is in the exponent spot. What's our base over here?
4.
Okay. Your goal is to try to make your bases the same, right? Now watch carefully. If you get that, great. But that's not the only thing we're doing today. So you still got to be focused on this next stuff here. There's some other manipulation we can do. Can you write this as 4 to some power? Don't you give me 4 squared. Because 4 squared is 16, right? Can't do that. Can't go, oh, 4 to the x equals 4 squared. How bad? Yeah, x is 2. No, it's not 2. Why? If you plugged in 2, you get 4 squared equals 8. Does that make sense? No, you can check your work here, right? You should be able to plug in those numbers and they actually work out in your original equation. It does here, it does here, it does there. 2 to the 4th is 16. 5 to the 3rd is, well, 125. Here, we got to change both bases. So occasionally you'll come across a problem where it doesn't look like you can make common bases out of it. Well, this one, you can't write this as 4 to any power. However, do they both have a base that you could write it in common? Yeah, how could you write this one? Think about a smaller base. How could you write 4 as a power that this one could share as well, as a base that one could share as well? You could write this 4 as a what? 2 to the what power?
Second.
Okay, so instead of thinking of this as 4 to the x, I can think of it as 2 squared to the x. Is that still the same thing as 4 to the x?
Yep.
So you're still looking for a common base, only this time you've got to look for it within those numbers. How about 8? Can you write that as 2 to some number? 2 to the 3rd. Okay, I need to show of hands how many people were able to follow that one. Good, okay, so you can't go directly for the 4 here. You can't write that as 4 to any power. Here, though, you can write this as 2 squared and 2 to the 3rd. That does have the common base of 2. You with me on that? Now, this is going to take just a little bit more work on this side, a little bit more work over here. What do you do when you have a power raised to a power? Do you add? Do you subtract? Do you multiply? Do you divide? Which one? I only have a couple people saying that. Are y'all familiar with that? That is multiplication there? So instead of 2 to the 2nd to the x, could you do this? Could you do 2 to the 2x?
Yep.
What's 2 times x? You're multiplying those, right? 2 times x is 2x. Equals 2 to the... That side we didn't have to do anything on. Hey, look at the board. Do you have common bases now? That's awesome. What do you know about our exponents? If our bases are the same, what do you know for a fact about your exponents? They are equal. Look what we did over here. We had common bases, exponents were equal. We made common bases, exponents were equal. We made common bases, exponents were equal. We now, with a little bit more work, we made common bases, but what this means is that your exponents have to be equal. You can essentially drop your bases if they are the same in your equation. That's what we've done. We've said, oh, bases, those are the same thing. That means our exponents must be equal. That lets us go from here to here. Would you raise your hand if you're okay on that problem so far? Yes?
How 2x is equal to 3?
Well, this is my exponent, right? And that's my exponent. You know, if your bases are the same, your exponents must also be the same. It's got to be there. Just like over here, x was equal to 4, x was equal to 3. 2x is equal to 3 in this case. Now, are you done? What do you got to do now?
Divide the 2 from the x.
If you do that, is it okay to get a fractional exponent?
Yep.
Yeah, in this case, that means a square root of whatever that is, a square root of 4 cubed. That's what that means. It's a 3/2 power. Remember talking about roots and exponential powers like that? That's what we've done. If you take on your calculator and you do 4 to the 3/2, you're going to get 8. If you do it in your head and you go, okay, the square root of 4, remember the square root, what's the square root of 4?
2.
Now raise 2 to the 3rd power, what do you get? You get 8. That means that works out. That is the equation there. That's a solution for our problem. You still with me on this? Okay, let's try one more together. I'll give you a few to do on your own. Can you see how when you get the hang of this, this is kind of fun? It's kind of neat. Well, I like it. Okay, just always remember your goal. Your goal is to try to make those bases identical. That's what you want to do. So the first thing you look for is, do you already have some number that you can make the other base into? Well, for instance, here we had 2 and 16. That was great. We had 5 and 125. That was great. 4 and 8 we could not do that with. You can't write 8 as any power of 4. Here we've got 9 and we've got 27. Can you write 27 as a power of 9? Really?
Oh, no.
No, it's power 3.
I mean, if you try 9 squared, you're getting 81, right? So, I mean, you can't do that. However, can you look for a number within 9 and 27 that you could write both of them as some power of?
Yeah.
So you go 9, 27. Those should have a common base somewhere in there, otherwise you can't do this problem. So you're always looking for that. What number do they share as a base? 3. Okay, 3. So now I want you on your paper to translate 9 into a power of 3 and 27 into a power of 3. Do that for me. What's 9? 9 is 3 to what power?
3.
3 to the what? And 27 is 3 to the... Did you make it that far? Okay. Now, of course, we still have this stuff going on, so watch carefully on this. This was just our 9, right? This is still our 9. So we still have this x minus 1 up there. You with me? And this was 27, but we still have our x up there. Little head nod if you're still okay. Yes? Yeah. You guys are here? Yes? Yes? No?
Yes.
Okay. What do you get? So we're okay getting 3 squared. We're getting 3 to the third. We didn't change this at all yet. What do you get when you have a power raised to a power again? So tell me on my right-hand side what I need to have. 3 to the 3 times x. Yes? Not 3 plus x, 3 times x. We're multiplying those exponents. Now on the right-hand side, this one's interesting. Take a little bit of time to think about this for a second. We've got 3 squared to the x minus 1. Again, just like this side, what do you do when you have an exponent raised to an exponent?
Multiply it.
So we're going to have 3. Do I write it like this?
No.
Oh, no, because this is my entire exponent, right? It really should have some parentheses around the thing. It really should, because that's my exponent. So when I take my 2 and I multiply it by x minus 1, well, wow, you better have some parentheses there. Do you see why them parentheses are important? I think I just said, do you see why them parentheses are important? We're in Alabama. It's math. We in Alabama. We're not Alabama. See why them parentheses are important? You know, when I was 13, I went around the country with my parents in a motorhome. We spent a lot of time in Texas, and because Texas is freaking huge, a lot of time in Texas, Louisiana, Alabama, and Florida. And when you're 13, you pick up accents very quickly. And by the time we got home, I still had an accent for about 5 years. I still have it sometimes when I'm talking. I say y'all all the time. I'm from Clovis. That's weird. It's weird. Anyway, we got 3 to the x, we got 2 to the x minus 1. What do you know when your bases are the same? What do you know about those exponents? Well, look what happens. As soon as we get those 3's right here and right here, if you want to cross them out, you can do that. I don't care. But what this comes down to is that now we have an expression 2 to the x minus 1 equals 3x. We have this exponent, that's an exponent, equals that exponent. Do you see how we're getting from here to here? Do you see how we're getting from here to here? That's kind of an important one. You know what people always do? They always give me 2x minus 1. They forget to distribute that. That's why I'm having you write the parentheses, and wait till this step to distribute. That way you don't forget to do that. You with me? Can you solve that? Sure, that's a basic equation. I mean, that's pretty easy. Of course you're going to distribute. You're going to get 2x minus 2 equals 3x. We'll distribute that 2. You'll subtract 2x. Negative 2 equals x equals negative 2. You can plug that in and you can check it. It's going to work out for you. Would you raise your hand and feel okay with this so far? Yes, no?
Yes.
Yeah. You guys over here? Try 3 of them on your own. We'll move on.
Are the 2 bases always going to be given to you?
The 2 bases are not going to be given to you. Here they weren't. But you had to...
Are you going to have like both numbers on either side of the equal sign at all times?
You have to. Yeah, exponential, you have to have those numbers there. So you're going to be given numbers. And in this section, your only job is really to find out what number you can find to make them equal bases. That's your only job here. Okay, this last one is a tricky one. You really got to think about that. I'll give you a hint. Think about negative exponents for that. So that's a tricky one. So try those ones. I expect you're rock solid on the first two of them. The last one is going to be you're going to have to really think on that one, but we'll do that one together if you can't get it, okay? So let's take a couple minutes. Things go pretty quick. Go ahead and solve this. By the way, when you're done with those, take out your calculator because you're going to need it here real quick. You guys done for the first two? Okay, let's go ahead and start the next. So first one, some of these you can do in your head. I still want you to show the work. Because I mean, 3 to the x equals 9, you're thinking, well, that's obviously a 2, right? It's obviously a 2. But the idea is get your bases the same, because you probably can't do that one in your head. If you can, well, good for you, but that's pretty hard. You got to think about it. It's probably take you longer to do it in your head than actually work it out. So here we'll go, okay, I know I can do 3 to the x equals 3 squared because I'm going to try to write 9 as a base of 3. I need my bases equal. But as soon as you have those bases equal, you also know your exponents are equal. Set them equal. If you don't have to do any more work, you're done. If you do, like the next example here, well, I know that I can't write this as 25 to any power, but I can write them both as 5 to some power. This one we did earlier in the day, that's 5 to the third, then to the x. This is 5 to the second, and then to the x minus 2. Hands, how many people made it that far? Good for you, that's good, okay. So 125 is 5 to the third, 25 is 5 squared. We haven't done anything with those exponents yet. Then your goal is to realize that, well, if I have an exponent raised to an exponent, that means I'm going to multiply it. So instead of 5 to the third to the x, I've got 5 to the, is it 3 plus or 3 times x? So that would be 3x. Did you get 3x? Equals, on the other side, I've got 5 to the, I have a 2 being raised to the exponent, but it should be like this, 2 to the x minus 2. 2 to the x minus 2. Why do I have parentheses right there?
Multiply.
We're multiplying by the entire exponent. We have to do that. But as soon as you have those bases the same, notice how our 5 and our 5 are the same exact base in this case. That's why we did this work, to get down to the 5 equals 5 as far as our bases. Then you can set your exponents equal to each other. 3x equals 2x minus 2. Of course, we'll distribute. Subtract 2x. X equals -4. So again, the whole goal here, try to make your bases the same. As soon as you get them the same, take your exponents and multiply them. Because you have an exponent raised to an exponent, that's what exponentials do. So multiply 3 times x and 2 times x minus 2. You might have to distribute there, then solve it with a basic equation because now your bases will be the same. You set your exponents equal, work all the way down. How many will feel okay with what we talked about? The idea at least. The idea. Okay. Now the last one. The last one's tricky. Last one's tricky. Because you look at that, you go, I've got 1/4 to the x. I've got 16. Now, you do have a couple options here. The first option, you could use a 4. You could use a 4 as your common base, or you could use a 2 as your common base. Are you with me on that? You have options here. They'll both work. They will both work. I'm going to show you the 2 version because I want you to be able to do other problems besides just this one type, okay? Here's the version using 2 as a common base. First thing, do you see that 2 is a base between this and that number?
Mm-hmm.
Well, do me a favor. Write it like 1/2 squared to the x equals 2 to the 4th. Is that okay with you? Yes, no? That's still 1/4, that's still 2, I'm sorry, that's still 16. 2 to the 4th is still 16. Yes, no? Now, I gave you a hint. I said, think about negative exponents. Check this out. If you have 1/2 squared, I need you to understand this is the same thing as 2 to the -2 power. Do you see that if I move that to the top of my fraction, I can change that that exponent to negative, and it means the same thing? You with me on that? You could go from here to here, couldn't you? That is 1/2 squared. That's what that is. So go in reverse. Hey, now we have something we might be able to work with. In our case up here, we'll have exponents raised to exponents will multiply. You're going to get 2 to the -2x. See where the -2x is coming from? You're multiplying there. Equals 2 to the 4th. Do you have common bases now? Yeah. Set your exponents equal to each other. We've got -2x equals 4. What are you going to do to get rid of that -2? If we divide by -2, you get x equals -2. So when you're faced with those fractions, don't just give up. Do the same thing. Only when you have something on the bottom, your denominator of a fraction, make it a negative exponent. Move it to the top of your fraction. Could you guys follow that one? That's a little trickier, but it's possible for you. Now, the last thing we'll talk about in this section is something called interest. Have you guys ever bought anything on credit?
Yes.
No.
Do you have a credit card? How many people have a credit card? Then you bought something, you probably paid a little bit of interest, right? Unless you pay off your statement every month, you pay interest. Now, I try to pay off my statement every month because I hate paying interest. That's giving away your money, right? Just for the sake of getting it sooner because you want it now. Right? Everyone does this though. People buy cars without all the money because cars are expensive. You ever bought a car before? Oh my gosh, they're ridiculous, all right? You pay $25,000 for a car, you drive off the lot and it loses $5,000, just like that. Just from driving it off the lot, you lose like, I don't know what percentage of the money it is, that would be 1/5. 20% of it, but it's not that much right off the bat. Anyway, you're losing some of that value, but if you buy the car without all the money, you're going to pay interest. You read those ads, 2% financing, 5% financing on your vehicle. If you buy a house, everyone has mortgages right now, right? And you have interest rate for your house. That means every month you pay a little bit of interest so that you can live in this place because you borrowed the money from the bank. We're going to figure out how to do something called compound interest. Here's what compound interest does. Compound interest can work for you or against you. Do you guys have bank accounts?
Yes.
You have money in your bank account?
Yes.
What's your account name? Just kidding. But in your bank account, you get a little bit of interest each month, don't you? You ever looked at your statement? It says at the very end, oh, you made 0.01 cents this month. Congratulations, you have no money. Right? So, I mean, even if you have a lot of money, the interest isn't very great. You get like maybe 10 cents a month because they say, well, here's your reward for saving your money with us. We're going to give you a percentage of your money. That's called interest. And here's how compound interest works. Let's say you start, let's do a very optimistic example. Let's say you start with $1,000 in the bank. You with me? And let's say your interest is compounded monthly. At the very end of the month, they're going to say, oh, we're going to give you a percentage of that money. Let's say we give you $1. That'd be a pretty good interest rate right now. So let's say we'll give you $1 for having $1,000 in the bank. Well, at the end of the month, then you're going to have $1,001, true? If you don't put any other money, you don't take anything out, you're going to have $1,001 at the end of the next month. You agree? They're going to give you interest on $1,001. So they're going to give you interest on top of what they just paid you for it. That's called compounding. So they're adding interest to your interest. So that they add it to your account, then you get interest on that amount. Then it knocks you up a little bit, then you get interest on that for the next month. That's being compounded. Do you understand the idea of compound interest? Same thing with the credit card, okay? Let's say you bought something for $10,000 and you don't pay anything. They're going to charge you interest on that $10,000 at the end of the month. Then the next month, you'll get charged not only for the $10,000, but the $10,000 plus the interest they tacked on there. And it's going to keep building very, very, very fast. That's compound interest. Now, how we use this is this formula up here. You need to know what the letters stand for. The letter A stands for the amount that you're going to have in your bank account or the amount that you're going to owe after a certain amount of time. So this is your amount. P, that letter P, stands for principal. Not principal like the guy, okay, not the guy that gets you in trouble in high school or something. Not that type of principal. Principal like this is the amount that you put into the bank at the beginning, or the origination of your loan. So it's the amount that you're borrowing or the amount that you want to save. That's what you start with. Now, I always misspell principal, so I hope that one's right for you. It's either AL or LE. I can never remember. I think it's the LE. Pretty sure. Yes? Okay, good. Pass. R. R stands for your interest rate. It's going to be in a percentage. N's an interesting one. T's pretty easy. T is the time in years. The years you're going to have that loan or the years you're going to have your money in the bank without touching it. N. N is the number of compounds per year. So let's imagine this for a second. If I say it's compounded annually, how many times is it compounded per year?
Once.
Annually means once. Semi-annually would mean twice. Quarterly would mean how many times? Monthly would be how many? There's 12 months in a year. What if I said weekly? How many weeks are there in a year? That'd be compounded 52 times. How many days are there in a year? So if I said daily, it'd be compounded 365 times every year. You with me? So the number of compounds per year. Now you're going to need a calculator for this because you're not going to be able to do this in your head. Let's go ahead and make up an example. You're going to buy let's say a cheap car. All right, you're going to buy a used car up here. How many years do you want your loan for?
6 years.
6 years. Great. 6 years. How much do you want to buy a car for?
40.
$40,000? Are you crazy?
Okay, 34.
I said a cheap car.
Oh, 20.
6,000.
12. Okay, 12,000.
It's a cheap car.
Hey, I bought my car for $7,500.
Oh.
And that thing floors. Oh my gosh. It's got twin turbos. It's 0-60 under 5 seconds.
Get the new one.
It'll beat a new one.
Just get the new one.
Why?
It's prettier.
So find the amount owed at the end of 6 years if $12,000 is loaned at a rate of, what interest rate do you want to pay?
0.
Oh, you want to pay 0? Yeah, of course. That'd be awesome. But you're not going to pay 0.
Why not?
Because they ain't going to give money for free right now.
349 or something. Realistic.
Let's do something easy like 5, okay?
Oh.
5%. Let's say your credit's not that great, okay? They're not going to give you 2.9% financing. They're going to give you 5%. And compounded, usually when you pay auto loans, it's compounded monthly. That is how a problem would look. That's how a problem would look on a test. So guess what? Yeah, a problem like that on a test. Find the amount owed at the end of 6 years if $12,000 is loaned at a rate of 5% compounded monthly. Can you fill out that formula with those numbers? This is the only example you get, so hopefully we get this one right the first time. First thing, do we know the amount? No, that's what we're trying to find. So we don't know what A is. Do you know what P is? P is your principal, it's how much you start with. How much did you start with here? So we're going to have $12,000. Then we have a parentheses because all we're doing is filling out that formula. That 1 never changes. And the plus never changes. How much is your rate? What would you say your rate is?
5%.
Now, are you going to put 5?
0.05.
Why are you going to put 0.05? So if I say 5%, 5% is 0.05. You with me on that? If you put 5, that's going to be like 500% interest. No one's going to pay 500% interest. Right? You'd be so broke buying this car, it'd be ridiculous. No, this is 0.05 because that is your rate. Rate is a percentage. You translate that to a decimal for your equation. Are you okay with that one? What is your N? N's the hard one that people get tripped up on. Usually percent is fine unless they just do 0.5. You're not going to do 0.5, you're going to put 0.05. Monthly, compounded monthly, this is how many times you were compounded a year. How many months are there in a year? So you're going to put a 12 here. Also, notice that your exponent is n times t. And so you're using that number twice. If you have 12 here, you're also going to have 12 here. That's your n times t. What's your t in this case? 6 years. Okay. How many people feel okay with filling out the formula? Now that's all great, but you got to be able to do the math right on your calculator. This is a calculator problem more than a math problem. Here's how you do it without having to round, because you cannot round this. If you're up, let me ask you a question. If you're in the car business or banking business, and you go, well, I don't really know how to work that right, so let's just round it. Are you going to be in that business very long?
No.
If you're off by a penny, you're probably going to get fired, okay? Because banks don't mess around. They want to the penny accurate. So I want to the penny accurate. So you can't round any of these numbers. None of them. Are you with me? You can't round any number. The only thing you're going to do first, without doing this all in one step, I'm going to show you how to do this all in one step right now. You're going to want to know that, right? Because you want to write down a whole bunch of long numbers. This is how you do it all in one step, besides the first one. The first one is figure out what that number is first. It'll usually be something pretty easy, like 12 times 6, or it'll be an integer number. It'll be a whole number. 12 times 6, 12, 72? 72? So you're going to write down 72. Now follow me carefully. Here's how you do this all in one step. Just listen to what I'm going to talk about. You're going from the inside out. We're going to do this a little bit different than how it's written. First thing you're going to do, you're going to do this one. So on your calculator, plug in 0.05. You got it? Divide by 12. Press equals. Add 1. So plus 1. That's you right here right now. Press equals. You should have 1.0 something. 004. You should have 1.004. Do you have that?
Mm-hmm.
Okay. Now find your exponent button and say to the 72nd power. That's why you need a calculator. To the 72nd power. So to the 72. Did you get that?
Mm-hmm.
Press equals.
0.34.
How much?
0.34.
0.34? Anybody else have 0.34?
To the second power?
To the 72nd power. 72nd. So to the exponent 72. Should be 1 something.
It's 1.34.
1.34 something. You got that? Now after that, multiply by 12,000.
16.
Press times 12,000, then press equals. And that will give you the amount that you're owed all in one step. If you didn't catch that the first time, watch that video again or come and see me after class and I'll show you how to use your calculator. How much is it?
16,188.
Point what?
21.
Is that rounded correctly? Okay. You need it to the penny accurate. Now, this is what this implies though. This is not a realistic example because when you have a car loan, you usually pay some each month, right? So, I mean, you're not going to owe this at the end of 6 years. This is how much you would owe if you didn't pay anything. And they said, you don't owe us a dime. Just wait for 6 years and pay it all off right then. Okay? That's how like the furniture stores work when they say, you don't owe us anything, no interest, no payments for 4 years. Then at the end of 4 years they go, now you owe us the money. And you go, my couch is a piece of crap now. I don't want to pay you $5 grand for my couch. It sucks. They go, Sorry. Yeah, that's how they work. Car companies usually don't work like that. They say you owe us a little bit each month. That way you don't just default at the very end and say, I'm not paying you a dime. Haha, take the car back. It sucks now. So they're not going to do that. How many people understand our idea here? Now, the only other thing I got to show you with this section is, this is the thing, everything can change, but this will change the value of your amount. What if I said now compounded daily or weekly? Let's do daily. If I do daily, what does our n change to?
360.
Nothing else would change. Now, if you want to do that real quick, once somebody do that, I'll write down what weekly and semi-annually mean for you. Do that real quick and find out if this is much different, okay? So do the same operation that you did. Of course, you're not plugging in 72 now, you're going to plug in 365 times 6. Did anybody get it?
Yep,
Should be 16,000, like 200 something.
almost.
What is it?
It's 16,197, 197. Almost there.
Wait a second. I want you to think about this for a minute, okay? Look at the board with me. This is compounded 12 times a year, right? That means that only once a month do you get the interest tacked on for your payment. This is compounded every single day of the year. Is it much different?
Not really.
No, it's not. It's less than $10. Okay, $10 difference after 6 years. So is it the compounding that actually makes you the money?
No.
Or charges you the money?
It's the rate.
No, the biggest thing is the year, well, of course the years, okay, and the interest rate. If the interest rate changes, that changes how much you owe a lot. But if your bank goes, hey, we're giving you interest every single day, it's not that great, okay? It's not going to be a whole lot different than compounded monthly. It's not going to be all that much extra. Have you understood what we talked about today?
Good. You get me enough for a big night.